Hello, this is question 6 on your June 2023 paper 3 from Edexcel. It's a mechanics question, it's a moments question. So you have a rod AB, has mass m, length 2a. So we know the whole length is 2a. And then we have the mass is m. The rod has end A on rough horizontal ground and end B against smooth vertical wall. So the ground is rough and the wall is smooth. We have an angle of theta here and is addressed in limiting equilibrium. Yeah, limiting equilibrium is telling us that the friction is going to be maximum. Yeah, this is telling us that this is in equilibrium, but friction is going to be mu normal reaction. State the direction, left or right, of the frictional force acting on the rod at A. So if we think about the forces that we have, let me see if they say the rod is uniform. So I'm going to draw the weight in the midpoint because it's uniform. The weight is going to be the mass, which is m, multiplied by gravity, and then I have friction here at A, normal reaction perpendicular to the ground always, so R, and normal reaction perpendicular to the wall at B. So there are a couple of ways of thinking about this frictional force. You only have another horizontal force. If this is an equilibrium, the friction has to compensate this one. Yeah, so it has to go to the right, and that would be a way of explaining the direction of the friction. The other way, I think, is more intuitive, and is if you don't have friction, this bar will slip down. So the friction is preventing it from slipping down, and that means that has to go to the right. Yeah, so always the friction goes against the tendency of motion when there is no motion. So this bar would slip down if this is very slippery, which means the friction is stopping it, so it's against that. So this is the direction, and how you explain it is a bit up to you. So you can say that it's compensating the only other horizontal force, or is preventing the bar to slip down. Yeah, so if you see the marker scheme, they will offer both options. So we can write is to the right. Not only leave the answer in the sketch, I could write it, yeah, because they're asking you specifically to the right or towards the wall to compensate the only other horizontal force, which is the reaction S reaction at the wall. Yeah, so that's the first part. Then they say the magnitude of the normal reaction of the wall on the rod at B is S. Yeah, we call it S. By taking moments about A, show that S is this here. So it's 1/2 mg cot. We have to take moments about A, about this point. So remember, we take moments about A. These two forces, as they pass A, won't produce any moment. So I'm going to have this one and this one producing moment. This one is going to produce clockwise moment. And this one is going to produce anti-clockwise moment. Yeah, so one clock, one anti-clock, which means if it's in equilibrium, both are going to be equal to each other. Yeah, the clockwise equal to the anti-clockwise. So let me find them. Clockwise moment, this one is going to be the force multiplied by the perpendicular distance. So this is the line where the force is acting, right? So I need to find the perpendicular distance from the point perpendicular to the line of the force. So this is the perpendicular distance. This is the distance that I need. This distance, if you look at this right angle triangle, the hypotenuse is A because the length is 2A, and this is the midpoint. So this is A, and this is the angle, and this is adjacent. So this length is going to be A cos theta. Cos because it's adjacent to the angle. Yeah. So my clockwise moment is mg, which is the force. So moments about A is going to be must be 0. So the clockwise is equal to the anti-clockwise. The clockwise is mg times cos theta. A, which is the length of the hypotenuse, cos theta. That's going to be equal to the anticlockwise. The anticlockwise, I'm going to do something similar. So think about the line of the force. Let me clean this a bit. Line of the force, this force here is acting this direction, yeah? And this is the line of the force. So now I'm looking perpendicular distance from A to the line of the force, yeah? Perpendicular here. So if you look at this right angle triangle, this angle here is alpha, is theta, because they are alternate angles, yeah? So this is theta. And this distance that I'm looking for is opposite to the angle, right? So it's going to be sine. And the length of the hypotenuse is the length of the bar. So it's 2a. So this is 2a, and this is sine. So this distance is 2a sine theta. Yeah, 2a sine theta. And the force is S. So my moment is going to be S times 2a sine theta. If we make S the subject, we can cancel A. S the subject is going to be 1/2 mg cos theta divided by sine theta, and cos theta divided by sine theta is cot, yeah? So mg cot theta, and that's what we have to prove. This one here. Then the coefficient of friction between the rod and the ground is mu. Given that tan is 3/4, find the value of mu. Tan 3/4 is, well, we are not going to need that. No, I was going to tell you, remember this triangle where we have 3, 4, 5 is going to help us to find sine and cos, but we need cot, so it doesn't matter. Friction. We say is in limiting equilibrium, so the friction, this friction here, is mu normal reaction, yeah? So we know, because it's in limiting equilibrium, that means that friction is mu normal reaction. So my coefficient of friction is going to be friction divided by R. If we resolve horizontally, we know that friction to the right is going to be S to the left, and we just found S. So resolving horizontally, friction to the right is equal to S to the left, and we know that that is 1/2 mg cot theta. We just found it. If we resolve vertically, we know that forces pointing up are going to be equal to forces pointing down. So my only force pointing up, R, is equal to my force pointing down. And with these two, I substitute here, and mu is going to be 1/2 mg cot theta divided by mg. Cancel, cancel. That means that mu is 1/2 cot theta. Cot theta is the reciprocal of tan. Remember, cot is the reciprocal of tan, and we know the value of tan. The value of tan was 3/4. So cot is going to be 4/3. 4/3. So I have 1/2 multiplied by 4/3. So my coefficient of friction is 2/3. Yeah, that's mu. Then next, it says find in terms of M and G the magnitude of the resultant force acting on the rod at A. What is that force? Please don't get confused between resultant force and normal reaction, because sometimes you are. They are asking me the resultant force here between these two. So I have a force to the right, a force up, and I will have a resultant force here on A, acting on A. This one. This one is the one that they're asking me for. I'm going to call it F. They're asking me only the magnitude. And I know the values of friction, so I know the other two. I know R pointing up is mg, and friction pointing to the right is 2/3. No, what was that? It's going to be friction is 1/2 mg cot. So it's going to be 2/3 mg, yeah, 2/3 mg. And I have a resultant force. I'm going to use Pythagoras, yeah. So I need the magnitude of this force F. So the magnitude of F is square root of 2/3 mg squared plus mg squared, yeah. I can get the mg outside, doing the square root, and then I have 2/3 squared plus one more. So a is 4 9ths plus 1, 13 9ths, no? 13 9ths. Can do the root of that. So the magnitude of f is going to be root 13 divided by 3 multiplied by mg. Yeah, newtons. Always write the units when you have them. Yeah, so that's the magnitude of this force. That's what they're asking me. There's the combination between the friction to the right and the normal reaction up. And the last thing they ask is a new value for S is, in a new model, the rod is modeled as being non-uniform with the center of mass closer to B than A. So, center of mass before was in the midpoint, now is closer to B. So this force has moved towards B. And they ask, state whether this new value of S is larger, smaller, or equal to the value that S could take using the initial model. Give a reason for your answer. It's only 1 mark, you don't need to find that value. But if we move, so look at how we found S. We found S, so S is the moment of the weight divided by this. This is not going to change, yeah, because S hasn't changed and the position hasn't changed. What is changing here is this distance. So now, this, instead of being A, is going to be larger than A. So this has larger moment about A. So this here is going to be larger. So my numerator from S, my numerator is going to be larger. So S is going to increase. Yeah? S is going to increase. Is larger as the moment of the weight of mg about A is larger. Yeah, my numerator for S is larger. So this distance here is not A, it's a bit more than A. Yeah, before was A, now it's a bit more than A. Yeah, and that's it. That's all the question.